Even if Earth were perfectly still on the outside, no storms, no waves, no wind, the planet would still be roaring with motion from within, solid rock flowing like putty, continents drifting at the speed your fingernails grow, and a metal core spinning fast enough to power a planetary-scale magnetic shield. Everything dramatic we experience at the surface, volcanoes exploding, earthquakes shaking cities, continents sliding into each other, is just the visible turbulence of a much deeper engine. To understand why Earth's hidden depths matter, we need to see the planet not as a quiet rock with a thin hot center, but as a gigantic heat machine trying to cool down, and doing so in very particular, very violent ways. Start with the mantle, the thick rocky shell between the crust and the core. It's about 2,900 kilometers thick. That's the distance from New York to Denver, and it makes up roughly 84% of Earth's volume. It isn't a lava ocean, and it isn't rigid either. On human timescales, it seems solid, but over millions of years, it behaves like a very slow, very dense fluid. This mantle is heated from below by the core and from within by radioactive elements decaying: uranium, thorium, potassium. And like any fluid that's hotter at the bottom than at the top, it convects. Hotter, slightly less dense rock rises, cooler, denser rock sinks. These convection currents are unimaginably slow, a few centimeters per year, but they carry more energy than every hurricane, storm, and ocean current at the surface combined. Sitting on top of that convecting mantle are the tectonic plates, rigid slabs of lithosphere, meaning crust plus the very uppermost mantle. They're like raft fragments adrift on a sluggish, stone ocean. The plates move because the mantle below them is moving. Where mantle upwells, it drags plates apart. Where cold, dense slabs of plates sink back into the deep mantle, they pull the rest of the plate with them. The plates don't decide to move. They are passengers on the deeper flow. And that slow churning sets up the conditions for almost every major geological event we care about at the surface. Consider mid-ocean ridges, the vast underwater mountain chains that wrap around the planet like seams on a baseball. These are where plates pull apart, places like the Mid-Atlantic Ridge. As the plates diverge, pressure in the underlying mantle drops. Solid mantle rock, already hot, around 1,300 degrees Celsius, partially melts because lower pressure makes it easier for crystals to break their bonds. That melt, which is less dense than the surrounding solid, rises and intrudes into the gap between plates. Some solidifies underground, thickening the crust. Some erupts onto the seafloor as basaltic lava. This is volcanism directly powered by mantle convection and decompression melting. Without the deep heat flow, the ridge system, and the constant creation of new oceanic crust simply would not exist. On the other side of the tectonic conveyor belt are subduction zones, where dense oceanic plates dive back into the mantle. Here, earthquakes and volcanoes are not just random surface accidents. They are precise responses to the mechanical and thermal stresses of a sinking slab of rock thousands of kilometers long. As the slab descends, it drags against the overriding plate. The interface between them locks due to friction, storing strain like a compressed spring, sometimes for centuries. Eventually, the rock can't take the stress, fractures propagate, and the plates lurch past each other in a few seconds or minutes. That sudden slip releases energy equivalent to thousands of nuclear bombs. That's an earthquake. Its magnitude depends directly on how much of that deep boundary slipped and how far it moved. The seismic waves that race outward, P waves, S waves, and surface waves, are not just destructive, they are also messengers from the interior. P waves, or primary waves, compress and expand the rock-like sound waves in air and can pass through solids and liquids. S waves, or shear waves, wiggle material side to side and can only travel through solids. When large earthquakes occur, we can track how these waves speed up, slow down, or vanish as they pass through different layers of the planet. That's how we discovered the liquid outer core. S waves simply disappear when they hit it, because shear waves cannot propagate in a fluid. So every devastating subduction zone quake doubles as an extremely high-energy CT scan of Earth's interior. Subduction zones are also where some of the most explosive volcanism happens. As the sinking plate descends past about 100 kilometers depth, the minerals that trapped water in their crystal structures become unstable. They release that water into the overlying mantle wedge. Adding water to hot mantle rock lowers its melting point, just as throwing salt on ice lowers the freezing point. This flux melting produces magma that is more silica-rich and more viscous than the basalt at mid-ocean ridges. That thicker magma traps gases like water vapor and carbon dioxide. Pressure builds until it bursts out in explosive eruptions, forming volcanic arcs like the Andes, the Cascades, and the Japanese islands. So, the fire of these volcanoes is literally distilled from the water once locked inside an oceanic plate, carried deep into the mantle, and then squeezed back out. Not all volcanism sits on plate boundaries. Hawaii, for example, is in the middle of the Pacific Plate, far from any subduction zone or mid-ocean ridge. Its volcanoes are powered by a mantle plume, a rising column of anomalously hot rock, maybe originating near the core mantle boundary 2,900 kilometers down. As the plume head spreads out under the moving plate, it melts and punches through the lithosphere, building volcanoes in a chain that records both the speed and the direction of plate motion over millions of years. The Hawaiian Emperor's Seamount chain even curves sharply, a fossilized record of a change in the Pacific Plate's motion around 50 million years ago. Again, surface geology is just a shadow cast by deeper flows. If mantle convection is the engine that drives plate tectonics, the core is the dynamo that powers our magnetic field. One of the main reasons Earth is habitable. Beneath the mantle lies the outer core, a shell of liquid iron alloy about 2,300 kilometers thick, at temperatures around 3,000 to 5,000 degrees Celsius, and under pressures up to about 330 gigapascals. That's more than 3 million times the pressure at the surface. Deeper still is the solid inner core, a roughly 1,220 kilometer radius sphere of mostly iron, rotating at nearly the same rate as the rest of the planet, possibly slightly faster. The geodynamo, Earth's self-sustaining magnetic field generator, arises from the fact that this outer core is both electrically conductive and in motion. As Earth cools, the inner core slowly crystallizes, releasing latent heat and also expelling light elements such as oxygen, sulfur, or silicon into the outer core fluid. This makes parts of the outer core compositionally buoyant, so blobs of fluid rise, while cooler or compositionally heavier fluid sinks. These convective motions are twisted and organized by Earth's rotation through the Coriolis effect, aligning flows into spiraling columns parallel to the rotation axis. Because the fluid is made mostly of iron, it conducts electricity very efficiently. When you move a conductor through an existing magnetic field, you induce electric currents. That's electromagnetic induction, the same principle behind power generators. In the core, those currents in turn generate more magnetic field. The result is a feedback loop. Flow creates field, field influences flow. The combination locks into a large-scale, mostly dipolar field aligned roughly with the rotation axis. This magnetic field extends,